Alright kids, Daddy's been drinking again. So, you know what that means. We got another episode of Drunk Physics coming. Now, I have just been working with some of the coolest stuff I've done probably in my entire worthless life, but watch this noise right here that I'm going to start pointing out. Alright, we've been talking about matrices and tensors and waves and all of these sorts of wavy, tensory sorts of math things, but you have to have these things in physics. You just have to do it, alright? I mean, it's a really simple statement and it's unassailable. You have to have math things to do math things in physics, and one of these math things is this guy right here, a matrix. So just to show you how powerful these objects are, I want to show you a few things I've been playing with for the last couple of days, just working with matrix. Okay, so you have this idea of I and J when it comes to a matrix. Okay, those are your row and your columns. So I, comma, J. So I, J. So 1, 1, 1, 2, 1, 3, 1, 4. Or 1, 1, 2, 1, 3, 1, 4, 1. So either you have the one column or you have the one row. And then you have that all the way through the matrix. Those are matrices. These are useful damn things. They are so useful. They're that and like wave equations. You put these things together and they make powerful statements about physics. And I really wish more people actually learned more physics because they'd see things like this. So matrix 1, 2. So what is it? M1, 2. So I just asked this computer what is the 1, 2 of this matrix. So if this matrix were instead to have a 5 value right here, then if I asked the same question, it should have given me 5, but that's the point. This is the 1, 2 section here, the 5. Actually, I didn't actually change that in any real sense. Mathematica is fun to play with, but there are some rules, and I'm not really listening right now. Hold on, I'm not. Okay, had to pause for a second, but so this is going to turn into a rant. This is just going to be a long video with some post-processing, and I'm just going to talk about mathematical objects. So we need to start thinking, why do I have this why do I have this in the first place, this 4x4 matrix, okay? Well, that's a long way towards what I'm starting to think about. So if you have this object here, whether you have this -1, 1, 1, 1 time signature, so basically I was sitting here like playing with the matrix and trying to build it so it was a certain type of matrix, and eventually I figured it out. I figured out how to write this number so that it has this Minkowski metric. So we're going to type right here Minkowski. That's Minkowski. I like to use the I, but I mean if you wrote that in Russian, you'd see what I mean. It's Minkowski, which would actually look more like Minkowski. And then you have the backward ends. And this is an H, yeah, so Minkowski. It's this guy was a genius, okay? He had this identity matrix right here with 4x4. So -1 up here at the top. This gives the formulation for pretty much everything that has to do with space-time continuum stuff. Because in a certain sense, space, these guys down here, this part of the matrix, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, yeah, that thing I have in blue, that right there, this is completely independent of this part of the matrix or this part of the matrix. And to kind of zoom in, I'm going to make this a little bigger so you can kind of see what I'm getting off to. The Minkowski matrix. I just kind of made that sort of, actually no, I didn't. Now that looks like Russian, and like as English as you can write Russian. I know some Russian, so it's fun to play with. We're getting way off the tropic. Yeah, I'm subtropic here. What are we doing? Basically, I'm really drunk and I'm talking about physics and matrices and vectors. This is what I wanted to scroll down to, because now I want to show you vectors. There's this vector 1, 2, 3, 4. Alright, they all stack it up here for the programming thing, just so you can write it as a line. But what they're written as is 1, 2, 3, 4. This has this okay. We're gonna get somewhere with this. Actually, you know what? Let's talk about this little thing for a second, because this was cool. I learned to do this, and then I went, Oh, okay. So I basically just made a random integer matrix 100 by 100 wide. So yeah, it scrolls all the way over here and then all the way down here. It's huge. It's basically a giant grid of numbers. And they're all random numbers between 0 and 10. So this is just cool to see. I love playing with Mathematica, but like when I'm drunk or drinking or in some kind of intoxicated state, I just sit down and I play with this and I go, oh, that's cool. I didn't even know you could do that on a computer. So I came up with this static image, and it just turned out to be awesome because it shows like a range. It only has like what? I think there's 4, 1, 2, 3, 4. There's a lot of different colors here, but in its own little way, it kind of looks like the cosmic microwave radiation, where you have a little bit of variation and you can choose where you're varied between. And I thought, wow, if that doesn't look like a universe that I just made, where like, let's say these darkest bits here, let's say the color brown. The brownest bits have the most matter, okay? Because Black Lives Matter. The browner things matter, okay? Yeah, I threw that in there. You see what I did there? It was kind of, it's not funny, but it works. It works because, you know what? We need to start thinking about that stuff more. We need to start thinking about this racism and this thing where we need to start focusing on where the whiter things are. You know what? No. We need to start looking at the browner things. Way off topic, but I think it was a fun little rant for a second. But think about what that means. That's not racist. What I just said is that where there are more brown skinned individuals, okay, and when I say we, I identify with the not so brown people, because everybody's on this kind of spectrum between white and brown, all right? Now we're going to work with this. Give me 20 more seconds and I'll get to the point. Where there's more brown people, more white people look there and go, there's where all the brown people are. Now you can do it backwards too. Now they're going to make associations. And these associations are going to carry weight with them, and they're going to form your internal opinions about people who are brown or white or very brown or very white. Like, I don't know, transparent? Can people be transparent? The point is, let's start giving some weight in this particular equation right here to some brown areas where there's lots of brown. These darker areas here are pretty much the same as these lighter areas, okay? They just have like different places where they are because it's all random. It's completely random. It is 100 by 100. So 100 multiplied by 100. This is 10,000 pixels just randomly generated for fun. Okay, and I used it to illustrate a great racial point, which is that there's no such thing as race. There's just different values of white and not so white. Let's call it black. Because, you know what? Fucking rock on, dude. Black lives matter, and I am sick of these cops thinking they can do whatever the fuck they want. I'm going to make this political for a second because this is important to me as my identity as a person, being in a person's world and realizing that every single person on the street is just another person. They just have a different value, okay? They have a different value on some kind of spectrum where you're going to be more introverted, more extroverted, more this, more that, more skinny, more fat. Why do we care? The point is, people are people, so why should it be that you and I should not get along? Depeche Mode, I think that was. If that's not Depeche Mode, I don't know, seriously, just correct me. But we need to move on because this has been a 6-minute rant, drunk rant at that. Remember, this is drunk physics. This is now just became a drunk rant about racial barriers in society keeping us from actualizing our full potentials as a species to work together and actually do things that matter. And if that wasn't just the most empowering 5 minutes of your life, then, well, you'll find it somewhere, but it got me pumped up. Moving on. Okay, we just completely got off of mathematics. We have tensors, okay? Tensors are these things, okay? You can make a tensor like this, or you can make a tensor like, I don't know, somewhere up here I had something that's relevant to what I'm trying to say. Give me a sec. Yeah, I'm just... Okay, it was actually right beneath what I already stopped over. Look at this. 111, 112, 113, 114, 211, 212. It's this counting. It's this way of counting things and stacking them together in boxes and neat little piles of things that will, if you multiply through this, well, first you're going to start multiplying like by a column. So you're going to take these individual numbers, which is this, which you can replace this with a 0, okay? Tensors, I get these questions all the time. People want to know, like, what the hell is a tensor? Well, if this happens, watch. No. Wait. Oh, please. No. Okay, hold on. I just really messed up. Okay, what I just did in like 30 seconds happened in an instant of time, but I just changed this value right here to 0, 0. This whole column right here is now all 0 values. And what I just did is effectively make this whole column 0. This whole position. You see how that worked? So let's do it again. So I'm gonna show you exactly what I just did. So I erased all this, made this 0, and this. See, I have to do this stop-start thing for this, and it's actually kind of fun to play with. But I just made this. This equals this. Okay, 0. If it's all of these are 0, then none of these mean anything, and it's a 0 matrix. So once again, we're going to replace this with a 0. So we're just kind of playing with like an extended idea of a tensor. I just made this 0. And now we can just play with all of these values. You can just think of this whole block right here as, I don't know, somewhere between 0 and 1, or like 0 and -1, or whatever values you like with amplitude and so forth. But you can just start thinking of them as like, I need 4 values. M131, M132, 33, and 34, okay? Individual values. You need 4 values to make up this square right here, which is not actually square anymore. It becomes another vector. It's like a matrix made of vectors, which is a tensor made of vectors. All right, that's exactly what we just did here. This is a 4 by 4 by 4 array. It is a 4 by 4 tensor. All right. If I just did this, watch. I'm gonna take this out for a second. Now I just made a tensor, but then I add an element to it, 4 by 4 by 4, so now it's a 4 by 4 tensor made of 4 by 4 vectors. Every one of these M11 is going to become its own 1 by 4 vector, which just happened. See? Tensors are really cool to play with, but only if you have like computers, because if you're trying to do it on paper, nothing makes sense. You don't have this kind of switching on and off things that only computers can do, that the brain just hasn't seemed to figure out yet. That was cool. That was where I was wanting to go with all of this. But then we get down here and we start talking about how I don't know, I have a 0 over here and I have a 10 here, and they're like right next door to each other. But then I also have a 1 and a 9 there, right next to each other. I don't know how I found that, but that kind of worked well to illustrate my point. Is that, you know, everything is relative, man. It all works together in some physical way. But let's go somewhere important. All right, I started opening this up, and this is when I started really learning how to play with this in Mathematica. And I started making some of the most amazing things I've ever seen, and I made it. It's like art. It's like math art. And I mean, not to toot my own horn, but you're gonna see what I mean here in a second, because identity matrix 4. Okay, this is, if you do this, multiply this with any matrix, whatever B over, not BV, whatever B is, this whole thing equals B, okay? So this is your A right here, this matrix, and if you multiply it by any B in the world, you can have it whatever you want, it's going to be B. Okay, so if this equals -1, then it just equals -B. Wait, I don't know. I think I did that right. Linear algebra is really nuanced. There's a lot of things going into it, and you have to remember all of these subtle rules, because if you do it, and that's another thing I'm getting at, is if you put a 1 at any one point in this matrix right here, it's going to do something very, very different than if you had it do just this. Similarly, if you put like a point, let's see, I want this guy to be a 0.5. Okay, 0.5. I mean, any mathematician watching this or anybody who's done physics and knows like linear algebra just went, oh buddy, you just changed the whole graph. And that's kind of what I was getting at with this whole thing, is that I made this little brain toy. Look at this thing. Okay, this right here is just... When I saw this picture for the first time, it blew my mind because it started to solidify everything I already understood about what matrices do to vectors. Okay, so if I take this thing right here and I multiply it by a 4x4 vector that goes right here, txyz in this case, is space and time. So, 3 dimensions of space right here, xyz, multiplied into 1 dimension of time, so 3 plus 1 space-time. Everything, anybody who does these deep physics and knows physics has been like scrolling down and seeing all these equations and trying to see what I'm typing in, and they know what I'm getting after here. But the point is, if you have this matrix and it acts on a tensor, then, or you have this matrix and it acts on a vector. I want to say vectors are tensors. They're a specific group of tensors. You can multiply vectors by tensors, okay, because vectors are tensors. They're just smaller tensors. They're littler tensors. And you can have tensors which are a matrix made of vectors. Matrix, vector, tensor, these are all important points. Everybody who does physics and thinks about anything physical needs to understand what these objects are and how they work together and do things. I just don't know how to say that enough. I don't know how to say that enough times for it to really sink in, but you need to know what these things are. But the point is, so I have this vec1.tensor1 equals matrix form. You know, put this into matrix form for me. Basically make it into something in brackets. This bracketed mentality, it's everything. We are in the matrix because you can do everything in life with matrices, okay? We live linear algebra. Somebody has programmed this. And I'm not going to say like God is creating it, or, you know, it's not programmed by anything in particular, but there's a program that is followed, okay? There's a code that underwrites everything that happens in the universe. You call that God, you call it what you will, but it encodes the matrix, okay? And then you have this spiral, look at this, spiral out, alright? And it all comes away from the source, and it gets faster and faster the more it moves out. That's because I just started learning how to play with this. And now I have it squash in on these axes. Okay, no, stop. There, that's the view I wanted. Okay, it's squashing in on this axis, all the way from here and here, and then it's stretching out on this axis. So what's it do in the middle? Well, it doesn't do anything in the middle. It does absolutely nothing because you have a pressure here that's infinitesimal, pressure here, and then you have a stretch here that it works both of those out. So then then you have this, basically this is shear stress on the side, 1 unit of pressure in the y direction, and then shear stress. So shear stress on x and z, so it's stretching these sides of the thing, but then it's compressing on this side. Alright, that's how you can think about that. And we're going to get into a little bit more of this. We got a little bit of time to play with because I'm intending this to be 30 minutes. And if you're still here, you deserve to be here. And if you like what you hear, buy me a beer, man, because, like, cheers. I'm sharing this stuff, and it's really seemed to catch on. I'm thanking everybody who sits here and listens to me rant for a little while about nature, politics, physics, mathematics, music. You make up my customer base, but you also make up my ad revenue. So remember that every single 10 of you, I think, is like a penny. You're all like a tenth of a penny to me. So if I should think about you in monetary worth, you're worthless monetarily. But as people, who keep doing that over and over and keep supporting me, you become lots and lots of pennies, man. You're my money. You are my people that support me and keep me going and keep me wanting to do this thing. Because I don't know what I'm doing right now. I actually have no idea. But I want to move into this. I have some idea, okay? I do have some idea. This is all following a point. But actually, no. I'm going to wander off for a second, and we're going to look at periods and frequencies and amplitudes. All of this is changing in time and space. You increase one amplitude, decrease one amplitude all the way to 0. So there's only one amplitude to work with. It just adds together. It becomes a tighter and tighter wave. Yet another frequency to it. Now it's like almost 1-to-1 rate. There you go, 1-to-1 ratio. And now you get it 1-to-1/2 ratio. You see this point where it starts kind of being like this. Well, let's expand these, alright, so I'm going to put in 1 and 2. Actually, that was 1-to-3. I should have known that. There you go. So this 1-to-2 ratio means like it has this point where it inflects. And we talked about this in another video, but this is important stuff to go with tensors and matrices, because you have to deal with these sines and cosines, and you have to deal with these periodic functions. And this is why I didn't choose to become a physicist. This is why I just understudied physics, because this stuff is tedious, man. You have to write the same damn equation out, I don't know, 17 times on a chalkboard and solve it for different variables that are changed. There's so much in physics that I don't want to do. That's why I went with engineering, because I want to build stuff. I want to make things. But this is how you kind of make music in a certain thing, in a certain way of thinking about it. So you have this 2-to-3 ratio, you have this 1-to-2 ratio. Now let's go with how maybe about, I don't know, 3-to-4 ratio. Well, okay, what is that? So now we have a 3-to-5 ratio. Now we have a 4-to-5 ratio. We have all of these different ratios of numbers to each other, and we can actually start to look at and objectively make assertions about how they are going to flip over each other in time in a certain sequence. You have to have, if you have a peak and a trough, they're going to cancel out. If you have a peak and a peak, they're going to double each other. So they're both going to be up here. Alright, off screen. I'm sure that was off screen. Point is, waves add to each other, and this is adding to waves, okay? So anybody who is looking at this and trying to figure out how I made this graph noticed this a sine pi times cx plus b sine pi times dx. So I stack this up so I can use these two levers here to manipulate, I love this, oh man, manipulate plot, okay? Mathematica, this is just how you design things to make awesome graphs, really awesome graphs. And illustrate larger points. That's the fun part. So A, B, C, D. Alright, so what is this d times x? Pi times d times x. Alright, right here. Sine of pi times d times x, which is also similar to saying sine of pi times c times x. So A and B are what then? Those are amplitudes, okay? If I do this, now I'm making one signal louder. Now I just completely canceled it out. There's only one wave going. But now I'm amplifying the signal of A to where it overpasses B, where I turn down B to the point where now B becomes A. B is no longer added to A because B is 0. Now you just have A. And now A gets quieter, and you have nothing, alright? So let's tie this together, because I have 5 minutes and some change left. We're going to put this together. Just bear with me here. This is going somewhere, I promise. I made a similar graph down here, and I kind of played with different variables, but at the same point, you have to learn, like, that when you have this tensor idea, okay? I want it to be this. Now, this is where I get to the meat and potatoes of it. Because now I have these really cool graphs. You're going to see this, and this is your treat for staying with me for 25 minutes. 1, 1, 1/2 1, okay? 1. This tensor right here. I said tensor 1 equals this graph, this matrix. I said vector 1 equals x and y. So this is going to act on x and y, and it's going to come out with this. Negative x plus y, x over 2 plus y. This is 2 dimensions. 2 dimensions that are working with each other. And when you have a vector field, this is 1, negative 1. So, I mean, if you plug that in, you would get this value where it's pointing over this way. But if you do it down here, it's the exact opposite. This is symmetric. Everything is symmetric on both sides. So this is going to get really hurried and really fun to play with. But now, if you sat with me this long, you honestly, like, sincerely have my thanks and my praise for sitting with me for this. This is the whole point. This is the end of the episode. This is me showing you what I just played with for 2 days and just went, oh my god, I understand everything. Alright. Tensor 1 equals negative pressure matrix. So diagonal components equal pressure. If you've watched my other videos, you know this already. Vector 1 equals 1, 1, 1. This is constant. This keeps it constant, or you can replace this with x, y, z. So we see this graph already, alright? We see every arrow is the same length, and it's pointing in the same direction. So I just gave a unit normal, okay? Once again, unit normal. Alright? Now we're going to replace this with x, y, and z. That means I just scaled it. I just scaled the negative pressure vector with x, y, and z. That means as it has, the further it gets out, which doesn't actually mean anything in the universe, the further it gets out, the more intense it is. And I think you can flip that by making this 1 over x. I've been playing with that for a little while and trying to make it make sense. But it basically means everything is pressing on the outside. It presses on the outside much harder than it does on the inside. All of your stress is, it's a stress tensor. This whole thing right here is just 3-dimensional stress tensor. So we're going to play with it for just a little while longer. Now check this out. Okay, that wasn't what I wanted to do at all. Yep, there we go. Okay. And now actually you get 2 graphs. So look at this. All of these are pointing in the same way. And there's no shear stress. There's nothing moving through these plates. It's just all moving in along their axes towards the middle. And then it stops at the middle. It doesn't... Gravity works the opposite way. It doesn't stop at the middle. It gets the most intense in the middle. Alright. So now we're going to talk about shear stress for a second. And now we're going to have shear stress. 1 second. Okay, these components of the matrix right here, these 1, 1, 1, where I have 1s, these all do one thing. And then this does the opposite. This moves it along their plates, parallel to the plates, and the zeros down here that go on the opposite side, they move through the plates. Alright, so we're going to look at this for a second. So I just basically made chaos. Alright, so everything is moving exactly the opposite way it should move. And so if it's all the way down in this corner, it's moving maximally off into the direction it's pointing. And if it's over here, it's moving directly down. If it's over here, I mean, everything's topsy-turvy. I mean, you can kind of just see as that rotates what I mean. It's shear stress. This is shear stress, and the entire point of it is to make things go this way. Alright? And you can see this down here as well. So now let's play with one more thing, and then I'm going to let you go and, you know, get you to the subscribe menu and all that stuff. And now this is momentum density in time, well, when it has time, but it's mass flux, I think. It sends everything this way, alright? It goes through this plate. You notice everything was along the plates before. Now it goes through this plate in the, what is this? I believe this is x XZ, I think it is. I'm pretty sure it's XZ. But we've pretty much run out of time. So, I mean, I'm gonna incorporate a little bit more into this, but you know what? I keep saying it, man. If you like what you hear, buy me a beer, and we'll do more drunk physics, man. Because this is some really fun stuff to play with. I keep doing this all the time, and it's magnificent every time I look at it, and I see these graphs that do these things, and I expected them to do it, and just to know that that's how the math works on things like this, where they're moving. I mean, it's a feeling only a physicist can get. And I'm not a physicist yet, but I'm getting there. And this has been Drunk Physics, because sometimes you just want to drink. You know what? Take care. Subscribe, like these things, click things. Just click things on my page. It makes me money. It's the only way I make money. Alright? Well, it's not the only way, but, you know. It's the only way I make money on YouTube. Just click things. Clicking things is cool. Do that all the time. Click all of the ads. Just pop them up for a half a second. It makes somebody a cent, and it makes somebody else a tenth of a cent for putting it up. Having it in the way of their product. That's how advertising works, alright? Just, they make money off of you knowing about their thing, and I make money off of them letting you know about their thing on my product, so I'm sponsored. I'm glad we got that out of the way. This has been another episode of Drunk Physics. This is just tensors stuff.